Right now, at the center of the galaxy you call home, something is waiting. You cannot see it. No telescope pointed at the right patch of sky will show it to you directly. No photograph has ever captured it in full. It exists in the precise location where the constellation Sagittarius rises in the southern summer sky, buried behind curtains of gas and dust, so thick that visible light cannot penetrate them. And yet, it is there. It has been there for billions of years, longer than the Earth, has existed longer than the Sun has burned. It sits at the gravitational heart of the Milky Way, 4 million times more massive than our star, occupying a region of space roughly the size of the distance between the Sun and Mercury. 4 million solar masses, compressed into a volume you could cross in minutes if you were traveling at the speed of light. That is what waits at the center of your galaxy. Its name is Sagittarius A star. Astronomers write it as SGA, times a notation that looks almost casual for something so extreme. And if you sat with that number for a moment, 4 million times the mass of the Sun, you might assume that what you're imagining is an object of incomprehensible violence, a cosmic predator, a void that tears apart everything that ventures near it, a churning mouth of destruction at the core of a galaxy that contains your world, your star, every human being who has ever lived. That assumption is wrong. Not entirely wrong, but wrong in the ways that matter. Sagittarius A star is for most of its existence quiet. Surprisingly, almost eerily quiet. It feeds slowly occasionally on wisps of gas that drift too close. The stars nearest to it, some of them orbiting at speeds that would carry them from one side of our solar system to the other in a single year, are not being consumed. They circle it, held in elliptical paths by its gravity, and they have been doing so for millions of years without falling in. The monster at the center of the Milky Way is in cosmic terms asleep. But here is what most people have never been told about black holes. The violence is not the point. The destruction is not the story. What black holes actually are, what they actually do, on the scale of galaxies and across the span of billions of years, is something far stranger, far more consequential, and in a quiet way, far more beautiful than anything the word destruction could contain. They are not simply the universe's way of ending things. They are, in ways that took decades of science to understand, and that still carry implications we have not fully absorbed, among the primary reasons that galaxies exist in the forms they do, among the primary reasons that stars form in the patterns they form, among the primary reasons that planets like ours exist at all, orbiting stars stable enough for life to have time to emerge. Black holes did not just kill, they built. That is the question at the center of this journey. Not what a black hole destroys, but what it creates. Not how it ends things, but how it shapes them. How something that swallows light, the fastest thing in the universe, the thing that carries all information across all distances, can be responsible for the structure of the cosmos itself. If you find yourself drawn to questions like these, to the kind of science that reaches down into the deepest assumptions you hold about how the universe works and quietly dismantles them, do me a small favor and hit the like button. Subscribe. It genuinely helps this channel reach other people who are lying awake at night, wondering about the same things, and there are more of them than you might think. Make yourself comfortable. Pull the darkness a little closer, because what comes next requires a particular kind of attention, the kind that does not rush, that lets things settle at the pace they need, that understands some ideas are too large to absorb in a single moment. Let's begin. To understand what a black hole is, you have to begin with what it is not. And what it is not, above all else, is a hole. The word itself misleads us. When we hear the word hole, we imagine absence, an empty space, something removed from the fabric of things, a gap, and that is almost exactly the opposite of what a black hole actually represents. A black hole is not the absence of matter. It is the most extreme concentration of matter possible. It is not emptiness. It is fullness taken to a point that reality itself cannot accommodate without bending. Consider what happens to a star. For most of its life, a star is a negotiation. On one side of the negotiation is gravity, the inward pull of the star's own mass, always trying to collapse it inward, to compress it into the smallest possible volume. On the other side is the outward pressure of nuclear fusion, the constant explosion occurring in the star's core, where hydrogen atoms are fused into helium, releasing energy in amounts so vast that the outward pressure of that energy is powerful enough to hold the star's own weight at bay. The star maintains its shape, its size, its warmth, because these two forces are in balance: gravity pushing in, fusion pushing out, an equilibrium maintained for millions or billions of years depending on the star's mass. Then the fuel runs out. When a star many times more massive than our Sun exhausts its hydrogen and then its helium and then the heavier elements it fuses, in desperation carbon, neon, oxygen, silicon, the fusion reactions that had kept it expanded simply stop. There is no more outward pressure, and gravity, which had been patient for millions of years, instantly wins. The collapse happens in less than a second. The outer layers of the star, suddenly unsupported, fall inward at a quarter of the speed of light. When they strike the collapsing core, which is now compressed to something the size of a city, a neutron star, the shockwave rebounds outward with enough energy to tear the star apart entirely. The explosion that results is called a supernova. It can briefly outshine an entire galaxy. It scatters the star's outer layers across light years of space, enriching the interstellar medium with oxygen, carbon, iron, calcium, the elements from which planets and everything on them will eventually be made. The calcium in your bones was made in a star that exploded before the sun existed. That is not metaphor, that is chemistry. But if the collapsing core is massive enough, if what remains after the explosion exceeds roughly 2 to 3 times the mass of the sun, then even the neutron star cannot hold. The neutrons themselves, particles that had been the last line of resistance against further collapse, are compressed past the point where any known force can stop the infall. The matter keeps compressing, past the density of an atomic nucleus, past any structure we have language for, into a point of infinite density that physics calls a singularity and that physics also quietly admits it cannot fully describe. Around that singularity, at a specific distance determined by the mass of the object, space and time, curves so severely that the escape velocity, the speed required to pull free of the gravitational field, reaches the speed of light, and then exceeds it. Nothing escapes it, not even light. That boundary, the surface of no return, is called the event horizon. It is not a physical surface. There is no wall there, no membrane you would feel yourself crossing. It is a mathematical boundary, a threshold in space-time, beyond which the geometry of the universe is so distorted that all paths, every possible trajectory, every direction you could travel, curves inward, toward the singularity. Forward in time for anything that has crossed the horizon is the same direction as inward toward the center. The event horizon is the edge of the knowable universe reproduced locally. Whatever happens inside it stays inside it, not because of any law forbidding communication, but because the structure of space-time itself ensures that information cannot escape. The inside of a black hole is in a very real sense causally disconnected from the rest of the universe. We can know nothing of what occurs there, not now, not ever. The man who first calculated this boundary did so under extraordinary circumstances. His name was Karl Schwarzschild. He was a German physicist and astronomer, and in November of 1915, while serving as an artillery officer on the Russian front during the First World War, while the mud and the cold and the death of the trenches surrounded him, he somehow found time to read Albert Einstein's newly published papers on general relativity. And within weeks, while still deployed in that war, he solved the equations. He found the exact solution to Einstein's field equations for the case of a perfectly spherical, non-rotating mass. He derived the radius at which gravity becomes inescapable. We call it the Schwarzschild radius in his honor. He sent his solution to Einstein from the front. Einstein was astonished. He had not expected an exact solution so quickly, and certainly not from a soldier in the middle of a war. Karl Schwarzschild died 4 months later from a disease contracted in the trenches. He was 42 years old. He never knew that the object his equations described would one day be called a black hole, a term that wouldn't even be coined until 1967. He never knew that we would one day photograph one. He never knew that the boundary he calculated would become one of the most consequential boundaries in the history of physics. The universe is indifferent to the timing of its revelations. For decades after Schwarzschild's work, physicists argued about whether black holes could actually exist or whether they were merely mathematical artifacts, solutions to equations that had no physical counterpart in reality. Even Einstein himself believed they were probably not real. The conditions required for their formation seemed too extreme, too perfect, too absolute. The universe, most assumed, would find a way to prevent it. The universe did not find a way. By the mid-20th century, observations of neutron stars, pulsars, and the X-ray emissions from certain binary star systems had accumulated enough evidence that the theoretical resistance began to crumble. What had been a mathematical abstraction became slowly an observational reality. And as telescopes improved, as detectors became more sensitive, as the capacity to observe the universe across multiple wavelengths expanded, the evidence became not merely suggestive, but overwhelming. Black holes are real. They are common. They are in fact ubiquitous. Every large galaxy we have ever studied appears to contain a supermassive black hole at its center. Not most galaxies. Every large galaxy. The Milky Way has one. Andromeda has one. The giant elliptical M87 at the center of the Virgo cluster has one measuring 6.5 billion solar masses. The behemoth at the center of galaxy IC 1101, that vast structure 60 times wider than our own, may contain a black hole exceeding 40 billion solar masses. Nothing escapes it, not even light. The universe did not produce a handful of these objects in rare circumstances. It produced them everywhere, at the centers of every major galaxy in numbers beyond counting across the observable cosmos. And their presence there at the heart of every galaxy we can see is not incidental. That fact sits at the center of everything that follows, not what a black hole destroys, what it builds, what it regulates, what it makes possible. But before we can understand what black holes do across the scale of galaxies, we have to understand what they are at the scale of physics. We have to go closer. We have to understand the geometry of the thing itself. What space looks like near the event horizon. What time does. What light does. We have to understand the architecture of the silence. And that requires going back even further to a man working in a Swiss patent office in the early 20th century, forming ideas that would eventually make Karl Schwarzschild's calculations possible. Ideas that would change permanently and irrevocably everything we thought we knew about the structure of reality. That story begins in 1905 inches Bern, and the ideas it contains are still more than a century later stranger than almost anything else in science. Ling Barsenjo. Claude responded. In 1905, a 26-year-old man working as a technical expert, third class at the Swiss Federal Patent Office in Bern, Switzerland, published 4 scientific. In 1905, a 26-year-old man working as a technical expert, third class at the Swiss Federal Patent Office in Bern, Switzerland, published 4 scientific papers in a single year. He was not a professor. He had no laboratory. He had no access to experimental equipment, no team of researchers, no institutional support of any kind. He sat at a desk, evaluated patent applications, and in his spare time he thought, the papers he published that year would each independently have been sufficient to make a scientist's career. Together, they constitute one of the most extraordinary outpourings of scientific insight in the history of human thought. One of them explained Brownian motion. One of them explained the photoelectric effect, for which he would eventually receive the Nobel Prize. One of them introduced the special theory of relativity, and with it, the relationship between energy and mass, expressed in an equation so compact and so consequential that it became the most recognized formula in science. His name was Albert Einstein, and in 1905 almost no one had heard of him. Special relativity told us something that seemed on its surface almost absurd. The speed of light is constant, not constant relative to the observer, not approximately constant under certain conditions, but absolutely invariably constant for every observer, in every circumstance, regardless of how fast they are moving relative to the source of the light. If you are standing still and a beam of light passes you, it moves at approximately 3,000,000 kilometers per second. If you are traveling in a spacecraft at half the speed of light and a beam of light passes you, it still moves at 3,000,000 kilometers per second relative to you. Not 4500000, not 150000. The same number. That constancy has a consequence that takes time to absorb. If the speed of light cannot change, then when something moves faster, something else must give. And what gives, Einstein showed, is time itself. A clock moving through space ticks more slowly than a stationary clock, not because of mechanical imperfection or some error in the clockwork, but because time itself, the rate at which the universe unfolds, is not the same for all observers. It is relative. It depends on motion. This was strange enough. But Einstein was not finished. 10 years after special relativity in 1915, he published the general theory of relativity. And if special relativity was strange, general relativity was something else entirely. It was a complete reimagining of the nature of gravity itself. Before Einstein, gravity was understood through Newton's framework. Masses attract one another. The strength of that attraction depends on the masses involved and the distance between them. The mathematics worked beautifully accurately, predicting the motions of planets and moons and falling apples with extraordinary precision. But Newton himself admitted he had no idea what gravity actually was. He could describe what it did, but not what it was. He called the apparent ability of masses to act on one another across empty space action at a distance, and he found it deeply unsatisfying. He wrote in a letter that the idea that one body could act upon another at a distance through a vacuum without the mediation of anything else was, to him, so great an absurdity that he believed no man who had any competent faculty of thinking could ever fall into it. Einstein gave gravity a medium, and that medium was space-time itself. General relativity tells us that space and time are not a fixed, rigid backdrop against which events occur. They are a dynamic fabric, a four-dimensional continuum that can be stretched, compressed, curved, and distorted by the presence of mass and energy. A massive object does not pull other objects toward it through some mysterious force acting at a distance. It warps the geometry of the space-time around it, and other objects moving through that warped geometry follow the curves. What we experience as gravity is the curvature of space-time. When you fall, you are not being pulled. You are following the straightest possible path through a curved geometry. The analogy most often used is a heavy ball placed on a stretched rubber sheet. The ball creates a depression, a curve in the sheet. A smaller ball rolling nearby will follow that curve, spiraling inward. That analogy is imperfect. It only shows 2 dimensions of a 4-dimensional reality, and it requires the concept of gravity to explain why the smaller ball rolls at all, but it gives an intuition for the idea. Mass curves space-time. Objects follow those curves. Now, take that intuition and push it to its extreme. A black hole is a region where the curvature of space-time is not gentle or moderate. It is absolute. The mass at the singularity is so concentrated, the geometry so severely distorted, that the curves of space-time do not just redirect things inward, they become inescapable. Every possible path through space-time, every direction, every trajectory ends at the singularity. The event horizon is the boundary of that region, the surface inside which all roads lead the same way. Imagine you are in a river swimming toward the bank. Upstream is the universe outside the black hole. Downstream is the singularity. Far from the center of the black hole, the current is gentle. You can swim upstream easily. As you approach the event horizon, the current strengthens. You have to swim harder. At the event horizon itself, the current flows at precisely the speed of light. To escape, you would need to swim faster than light. And since nothing can move faster than light through space-time, you cannot escape. Cross the horizon and the current becomes faster than light. It does not matter how hard you swim, what direction you choose, what technology you have. The downstream pull is not just strong, it is the structure of space-time itself. The singularity is not in front of you. In a meaningful physical sense, it is in your future, and you cannot escape your future. Nothing escapes it, not even light. The experience of approaching a black hole from the outside is itself extraordinary. As you fell toward the event horizon in a thought experiment, since no human technology has approached anything like this, you would notice several things. The first would be what physicists call gravitational time dilation. Clocks in stronger gravitational fields run more slowly. This is not a theoretical abstraction. It has been measured directly. The clocks aboard GPS satellites orbiting high above Earth, where gravity is slightly weaker than at the surface, run slightly faster than clocks on the ground. If engineers did not account for this difference, a difference of about 38 microseconds per day, GPS systems would accumulate errors of several kilometers per day. General relativity is not a luxury of theoretical physics. It is engineered into the technology in your pocket. Near a black hole, this effect becomes extreme. To an observer watching you fall from a safe distance, your clock would appear to slow down as you approached the event horizon. Your movements would appear sluggish, then almost frozen. The light from your body would stretch toward redder and redder wavelengths. Eventually, you would appear to stop completely suspended at the horizon, your image slowly fading as the last photons struggled to escape the deepening gravitational well. From your own perspective, you would feel nothing unusual as you crossed the horizon. For a sufficiently large black hole, the tidal forces at the event horizon, the difference in gravitational pull between your head and your feet, might be subtle enough that you would not notice the crossing at all. You would simply be inside, falling toward the singularity with no way back. For a smaller black hole, the experience would be dramatically different. Tidal forces, the stretching effect caused by gravity, pulling more strongly on the closer parts of your body than the farther parts, would become enormous near a stellar mass black hole long before you reach the horizon. Your body would be stretched along the direction of your fall and compressed laterally, the near side pulled away from the far side, faster and faster, until you were elongated into a thin strand of matter. Physicists call this process spaghettification. It is, in the literature, a technical term. The universe is not always subtle in its naming, but the question of what happens after you cross the event horizon, what happens near the singularity itself, is a question that general relativity cannot fully answer. At the singularity, the curvature of space-time becomes infinite, density becomes infinite. The equations that describe space-time so accurately everywhere else return values of infinity, which in physics is the mathematical equivalent of a raised hand and an admission that the theory has reached the edge of its applicability. Infinity in an equation meant to describe physical reality typically means we are missing something. What we are missing is a theory of quantum gravity, a framework that unites general relativity, which describes the behavior of the very large, the curves of space-time, the motion of galaxies, with quantum mechanics, which describes the behavior of the very small, the behavior of particles and fields at subatomic scales. These two theories are each extraordinarily accurate in their respective domains, and they are fundamentally incompatible with each other. They cannot both be correct in their current forms because in the extreme conditions of a black hole singularity, both are required simultaneously and they give contradictory answers. The singularity is where our best understanding of physics breaks down. It is the universe's way of telling us that our map of reality is incomplete. There is one place where quantum mechanics does have something to say about black holes, and the man who found it was in the 1970s, one of the most remarkable scientific minds alive. Stephen Hawking was a theoretical physicist at Cambridge University who had been diagnosed with motor neuron disease at the age of 21 and given 2 years to live. He lived for another 55 years, producing some of the most significant theoretical work in the history of physics during that time, communicating first through speech and eventually through a computer synthesizer controlled by a single cheek muscle. He worked in conditions that would have ended most scientific careers, and he produced, among many other things, a discovery so counterintuitive that it surprised even the physicists who understood its implications fully. He showed that black holes are not completely black. In quantum mechanics, empty space is not truly empty. At the smallest scales, the vacuum of space seethes with activity, virtual pairs of particles and antiparticles constantly flickering into existence and annihilating each other in intervals so brief they seem to borrow energy from the uncertainty in the measurement of time itself. Normally, these virtual pairs appear and vanish without consequence, but at the event horizon of a black hole, something different happens. A virtual pair appears at the boundary, and before the two particles can recombine, The curvature of space-time separates them. One particle falls inward across the horizon, the other escapes outward into the universe. From the outside, this looks like radiation being emitted from the black hole. It is called Hawking radiation in his honor, and its consequence is extraordinary. Because the energy of the escaping particle comes ultimately from the black hole's own mass, through a process too intricate to trace fully here, the black hole loses mass over time as it radiates. Slowly, extraordinarily slowly. A stellar mass black hole would take longer than the current age of the universe to evaporate by even a measurable amount. A supermassive black hole would take an almost incomprehensibly longer timescales measured in numbers that require exponential notation to write without filling a page. But the process is real. Given enough time, a black hole will evaporate entirely, and when it does, there is a problem. The problem is called the black hole information paradox. In quantum mechanics, information is conserved. The exact state of a quantum system can always in principle be recovered from the particles that interact with it. Nothing is truly lost. But if a black hole evaporates, and the Hawking radiation it emits is truly random, truly independent of whatever fell in, then the information about what the black hole swallowed is gone, destroyed, not scattered or encoded in some recoverable form, but erased from the universe entirely. This contradicts one of the foundational principles of quantum mechanics. And so for decades the question has remained open. What happens to information in a black hole? Does it escape somehow encoded in the Hawking radiation? Does it remain at the event horizon in some form we cannot yet describe? Does the black hole leave behind some remnant? The question has generated decades of work, including proposals by some of the most creative theorists in physics, including the firewall paradox, the complementarity principle, and the more recent suggestion that information escapes gradually, encoded in quantum correlations in the Hawking radiation that are themselves invisible to any individual measurement, but present in the totality of the radiation emitted over the black hole's lifetime. There is no settled answer. The information paradox remains one of the deepest unsolved problems in theoretical physics. It sits at the intersection of general relativity and quantum mechanics, which is to say, it sits exactly at the place where our understanding of the universe is most incomplete. Nothing escapes it, not even light. And perhaps in a way that physics is still working to understand, not even information itself. What we have described so far are the properties of black holes as they are understood from the outside, from the perspective of the universe that surrounds them. But to understand what black holes actually do in the universe, their role not merely as physical curiosities but as the engines and architects of cosmic structure, we have to widen our view. We have to move from the scale of a single collapsed star to the scale of galaxies. We have to look at the objects waiting at the centers of those galaxies. Not the stellar mass black holes formed from dying stars ranging from a few to a few dozen solar masses. Not even the intermediate mass black holes whose existence is still being established. We have to look at the supermassive black holes, the ones that weigh millions or billions or tens of billions of times the mass of our sun, the ones that sit at the gravitational cores of every large galaxy in the observable universe, whose presence shapes the structure of their host galaxies in ways that scientists are still working to fully understand. The ones that were already ancient when our galaxy was young. How did they form? How did they grow so large? How do we know they are there when we cannot see them? And how did they come to be so deeply entangled with the destiny of the galaxies that surround them? Those questions are where the story of black holes becomes the story of everything else. 0843. Claude responded, "There is a star called S2. There is a star called S2. It orbits something you cannot see. Its path through space is an ellipse, a closed curve that brings it screaming in toward the center of the Milky Way, and then carries it back out again over a period of approximately 16 years. At its closest approach, S2 travels at nearly 3% of the speed of light. That is roughly 7650 kilometers per second. In the time it takes you to blink, S2 has moved more than 15,000 kilometers along its orbit. Nothing in our solar system moves like that. Nothing near our sun could move like that, because nothing near our sun has a gravitational field powerful enough to accelerate a star to those speeds. The planets in our solar system move at tens of kilometers per second, not thousands. The difference is not a matter of degree, it is a matter of the nature of the object at the center of the orbit. For S2 to move at 7650 kilometers per second, the object it orbits must be extraordinarily massive. And for that object to be contained within the region that S2's orbit defines, a region roughly the size of our solar system, perhaps slightly larger, that mass must be extraordinarily concentrated. The combination of those two facts, the mass and the density required to produce the observed orbital velocity within the observed orbital radius, points to only one thing that physics currently knows how to describe: a supermassive black hole. The story of how we came to know this is one of the great slow detective stories in the history of astronomy. It unfolded not in a single dramatic moment, but across decades, built from thousands of observations, patient accumulation of data, incremental refinements of measurement, the kind of work that does not make headlines in any individual year, but which taken together constitutes one of the most rigorous demonstrations of an extraordinary physical reality that science has ever produced. In the early 1990s, two independent teams of astronomers began pointing their telescopes at the center of the Milky Way. The galactic center is not visible in ordinary light. The gas and dust that fill the intervening space absorb and scatter visible wavelengths before they reach us. But infrared light, with its longer wavelength, passes through more easily, and so these teams used infrared telescopes and later adaptive optic systems that could correct in real time for the blurring effects of Earth's atmosphere to peer through the obscuring curtain and observe the stars in the innermost regions of our galaxy. What they found was a cluster of stars moving in ways that nothing in ordinary astrophysics could explain. One team was led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany. The other was led by Andrea Ghez at the University of California, Los Angeles. They did not know it then, but they were embarking on a scientific competition that would last more than 2 decades, each team independently measuring the same stars, cross-checking and refining the same measurements, converging on the same extraordinary conclusion from opposite sides of the Atlantic. Year by year, they mapped the positions of stars near the galactic center. Year by year, the orbits became clearer. Some stars moved in arcs, others completed full ellipses within the span of the observational record. S2 was among the most dramatic, its orbit tight and fast, its closest approach in 2002, confirming what the data had been suggesting for years with a directness that could no longer be evaded. At the center of the Milky Way, within a region smaller than our solar system, there is a mass of approximately 4 million suns. There is nothing visible there. No cluster of stars that could account for that mass in that volume. No cloud of gas or dark matter dense enough to explain it. The only object that physics knows how to construct with that mass in that volume, the only solution the equations of general relativity permit, is a black hole. Reinhard Genzel and Andrea Ghez shared the Nobel Prize in Physics in 2020 for this work. They shared it with Roger Penrose, the mathematician, who had proved decades earlier, using the mathematics of general relativity, that the formation of singularities was not merely a possibility, but an inevitable consequence of gravitational collapse. 3 people, decades of work, a conclusion that would have seemed almost mythological a century before. The black hole at the center of our galaxy is real. Nothing escapes it, not even light. But knowing that a black hole exists and seeing one are two very different things. For most of the 20th century, and well into the 21st, all our knowledge of black holes was indirect. We inferred their presence from the behavior of the matter and light around them. We measured their masses through orbital mechanics. We detected the X-rays emitted by gas heated to millions of degrees as it spiraled inward. We observed the jets of energy they launched across thousands of light years. But we had never seen the black hole itself. We had never seen the shadow of an event horizon against the glow of surrounding matter. That changed on the 10th of April 2019. On that day, at coordinated press conferences held simultaneously in Brussels, Washington, Santiago, Shanghai, Taipei, and Tokyo, a collaboration of more than 200 scientists from 20 countries announced that they had done something that had been considered borderline impossible just a decade earlier. They had captured the first direct image of a black hole's event horizon. The object they imaged was not Sagittarius A star, the black hole at the center of our own galaxy. That object, though closer, is also smaller and more variable, its emission fluctuating on timescales short enough to complicate the imaging. Instead, they turned their instruments toward a galaxy called M87, Messier 87, a giant elliptical galaxy at the center of the Virgo cluster, approximately 55 million light-years away. At its heart sits a black hole of approximately 6.5 billion solar masses, 1,600 times the mass of Sagittarius A star. To image it, they built the largest telescope in the history of astronomy. Not a single instrument, but a network of 8 radio telescope arrays distributed across 4 continents in Hawaii, in Arizona, in Chile, in Mexico, in Spain, at the South Pole. Each array collected radio waves at millimeter wavelengths from the direction of M87. Through a technique called very long baseline interferometry, the signals from all 8 sites were combined, their timing coordinated with atomic clocks, accurate to within a fraction of a nanosecond, producing an effective telescope aperture, the size of the entire Earth. An Earth-sized telescope pointed at a shadow the size of a solar system located 55 million light-years away. The angular resolution required to resolve the event horizon of M87 times, as the black hole came to be formally designated, was equivalent to reading the date on a coin held in New York from a position in Los Angeles. It was equivalent to seeing an orange placed on the surface of the moon from the surface of the Earth. It exceeded at the time of its achievement the resolving power of any previous observational instrument in human history. The data collected during the observing campaign in April 2017, 2 years before the announcement, filled hard drives that could not be transmitted electronically. The data rate was too high for any internet connection to handle in a reasonable time. Instead, the drives were physically transported by airplane from each telescope site to processing facilities at MIT Haystack Observatory in Massachusetts and the Max Planck Institute for Radio Astronomy in Bonn, Germany. The South Pole data had to wait until the Antarctic winter ended and transport became possible. The entire dataset weighed approximately 5 petabytes, 5 million gigabytes of radio telescope observations waiting to be assembled into a single image. The assembly required new algorithms for image reconstruction, new methods for combining interferometric data from instruments separated by thousands of kilometers. One of the scientists who led the development of those algorithms was a 29-year-old postdoctoral researcher named Katie Booman, who had begun working on the imaging problem as a graduate student at MIT years before the observing campaign took place. She had written code designed to reconstruct an image from the incomplete and noisy data that an Earth baseline interferometer would produce, testing it against simulations and gradually refining it into something that could handle real observations. When the data was finally processed and the image assembled, what appeared on the screen was a ring of orange and red light, bright on one side and slightly dimmer on the other, surrounding a central region of darkness. The asymmetry in brightness, brighter on the lower left, dimmer on the upper right, is caused by relativistic beaming. The gas orbiting the black hole on the side moving toward us has its light amplified by its motion, while the gas moving away from us has its light diminished. The dark region at the center is the shadow of the event horizon against the glowing plasma of the accretion disk. It was exactly what general relativity had predicted. The size of the shadow, the shape of the ring, the degree of asymmetry. Every detail matched the theoretical expectations derived from equations written more than a century earlier by a man who thought such objects probably did not exist. Nothing escapes it, not even light. The image was not merely a photograph, it was a confirmation, a direct visual demonstration that the objects predicted by the mathematics of general relativity, the objects inferred from the orbits of stars and the behavior of X-ray sources, and the jets of energy they produced are real in the most fundamental sense. They cast shadows, they bend light around themselves in rings, they sit at the centers of galaxies, and they are in the strictest physical meaning of the word visible. Not in the light our eyes can detect, but in the radio waves that carry their signature across tens of millions of light years. The image released in 2019 showed M87 star in radio wavelengths. In 2022, the Event Horizon Telescope collaboration released a second image, this time of Sagittarius A star, the black hole at the center of our own galaxy, 4 million solar masses, 26,000 light-years away. The challenge of imaging SGR-A times was different from, and in some ways greater than, the challenge of imaging M87 star. Although SGR-A times is vastly closer, it is also vastly smaller. Its event horizon subtends a comparable angular size. It appears roughly the same size in the sky as M87 times, despite being 1,000 times less massive and much closer, but its emission fluctuates on timescales of minutes because gas orbiting it completes its orbit quickly, while gas takes weeks to orbit M87*. Gas near SGR-A times can complete an orbit in tens of minutes. Imaging something that changes faster than the exposure time is a challenge that required new computational approaches, new imaging algorithms designed to account for the variability. When the image was released, it showed the same structure, a ring of light surrounding a central darkness, the same physics, the same geometry, the same confirmation that what Karl Schwarzschild calculated in a trench on the Eastern Front in 1915 describes something real, something present, something sitting at the center of the galaxy that contains our sun, our planet, and every human being who has ever looked up at the night sky and wondered what was there. Now we know, and what we know is only the beginning of the strangeness. Because Sagittarius A star, for all its mass, is considered by astronomers to be dormant, quiet, underwhelming even by the standards of what supermassive black holes can do when they are actively feeding. The black hole at our galactic center is estimated to be consuming matter at a rate far below what its mass would suggest is possible. It is, in the language of astrophysics, severely sub-Eddington, operating at a tiny fraction of the luminosity it could theoretically produce. Other black holes are not so restrained. When a supermassive black hole is fed generously, when large quantities of gas fall into the accretion disk around it, compressed and heated to hundreds of millions of degrees before crossing the horizon, the energy released is staggering. Not all of the infalling matter crosses the event horizon. A significant fraction of it is converted to energy through friction and magnetic processes in the accretion disk. That energy has to go somewhere. It goes outward. In some of the most spectacular displays the universe produces, the brightest sustained sources of electromagnetic radiation in the observable universe are not supernovae, not gamma-ray bursts, not entire galaxies of stars shining together. They are actively feeding supermassive black holes. We call them quasars, and a single quasar can outshine the combined light of every star in an entire galaxy by a factor of hundreds or even thousands. The most luminous quasar currently known, designated J05294351, releases energy at a rate equivalent to approximately 500 trillion suns. 500 trillion. Our sun, which sustains all life on Earth from a distance of 150 million kilometers, outputs energy at a rate that a quasar exceeds by a factor that requires scientific notation to write without filling a line of text. And that energy comes not from nuclear fusion in a stellar core, but from the gravitational potential energy of matter falling toward a singularity. Gravity taken to its absolute extreme is the most powerful energy source in the known universe. Nothing escapes it, not even light. But what is generated in the attempt, what is produced in the region just outside the point of no return by matter that has not yet crossed it, is the brightest light there is. Quasars are distant not only in space but in time. The light we observe from them has been traveling for billions of years. We see them as they were in the early universe, when galaxies were younger and gas was more abundant, and supermassive black holes were feeding at rates they rarely achieve today. The universe's quasar era, sometimes called cosmic noon, peaked roughly 10 billion years ago. Since then, as galaxies have used up their gas and the supply of infalling matter has diminished, the black holes at their centers have quieted. Most of the supermassive black holes we observe today, including Sagittarius A star, are the sleeping descendants of those ancient blazing engines. They fed voraciously once, they grew enormous, And in growing, in consuming and radiating and launching jets of energy across hundreds of thousands of light years, they did something that transformed the galaxies around them, something that is only now being understood in its full implications. They shaped everything. Not merely the cores of their host galaxies, not merely the regions immediately surrounding the event horizon, but the entire structure of their galaxies, from the innermost regions to the outermost edges across distances of hundreds of thousands of light years. The black holes that formed and grew in the early universe did not merely consume what was around them, they regulated it, they governed it. They imposed an order on the chaos of early galactic formation that would not have existed without them. How they did this, the mechanisms by which an object that swallows light can determine the fate of an entire galaxy, is the next layer of this story. It is where the terror of black holes becomes something else entirely, where the singularity, the event horizon, the absolute finality of the inward fall reveals itself as only one part of a much larger function. The destroyers, it turns out, were building something all along. 0845, Claude responded. Begin with a question that seems simple until you sit with it. Begin with a question that seems simple until you sit with it. Why does the Milky Way have the number of stars it has? Not why does it have stars at all. We understand that part reasonably well. Gas clouds collapse under gravity, ignite nuclear fusion, and stars are born. That process is clear in its broad strokes. The question is, why does the Milky Way have roughly 2 to 400 billion stars and not 2 to 4 trillion? Why, given the amount of gas available in the early universe, given the immense clouds of hydrogen that filled the proto-galactic halos of forming galaxies, did the star formation process not simply continue until every available atom of hydrogen had been converted into a star? What stopped it? For a long time, astronomers did not have a satisfying answer. The gas was there, the gravity was there, the conditions for collapse and ignition were present, and yet galaxies did not convert all their available gas into stars. They converted a surprisingly small fraction of it. The efficiency of star formation across the universe, the fraction of available baryonic matter, ordinary matter, that actually ends up in stars, is estimated at only a few percent. The universe, despite having all the ingredients, is remarkably restrained in its star formation. Something is regulating it. The first clues came from observations that at first seemed unrelated to star formation entirely. Astronomers studying massive elliptical galaxies, the large red star formation dead systems that populate the centers of galaxy clusters, noticed something peculiar. The mass of the central supermassive black hole in these galaxies was not independent of the mass of the surrounding galaxy. It was correlated with it, tightly consistently across galaxies spanning orders of magnitude in mass. The black hole mass and the mass of the galactic bulge maintained a ratio of approximately 1 to 1,000. 1 to 1,000. The black hole is always roughly 1,000th the mass of the surrounding stellar bulge. This is remarkable for a reason that requires a moment to appreciate. The event horizon of a supermassive black hole, the region within which gravity is inescapable, is tiny compared to the galaxy around it. Sagittarius A star, with 4 million solar masses, has a Schwarzschild radius of approximately 12 million kilometers. The Milky Way is 100,000 light-years across. In proportional terms, the event horizon of our central black hole relative to the galaxy it inhabits is comparable to the size of a grain of sand relative to the entire surface of the Earth. Nothing that happens within the event horizon can influence anything outside it. Not gravitationally, not electromagnetically. The black hole's direct gravitational influence extends meaningfully only to the stars within a few light-years of the galactic center. The Milky Way is 100,000 light-years across. The direct gravitational reach of SGR A times encompasses less than 1,000th% of the galaxy's volume. And yet the mass of every supermassive black hole we have studied is correlated with the mass of the galaxy around it to a precision that could not be coincidental. Something connects them. Something links the tiny singularity at the core to the vast structure of hundreds of billions of stars that surrounds it. That something is energy. When a supermassive black hole feeds, when gas falls into the accretion disk and is heated to extreme temperatures, and a fraction of its mass is converted to electromagnetic radiation, the energy released, does not all fall inward. Much of it radiates outward, and in the most active phases of a black hole's life, that outward energy flux is not gentle. It is violent. It interacts with the surrounding gas in ways that can heat it, push it, accelerate it outward, and in some cases drive it entirely out of the galaxy. This process is called AGN feedback. AGN stands for active galactic nucleus, the luminous energetic central region of a galaxy that contains an actively feeding supermassive black hole. The feedback refers to the way that energy from the central engine propagates outward and influences the environment it was born from, like a feedback loop in an electronic circuit where the output of a system affects its own input. AGN feedback creates a self-regulating cycle between the black hole and the galaxy that contains it. The mechanism works in its broadest strokes like this. In the early universe, gas is abundant. It falls into the gravitational potential wells carved out by dark matter halos, concentrating toward the centers of forming galaxies. As it concentrates, it feeds the supermassive black hole growing at the center. The black hole grows. It feeds more vigorously. The energy output from its accretion disk increases. That energy in the form of radiation pressure, in the form of powerful winds launched from the inner accretion disk, and most dramatically in the form of relativistic jets of plasma launched perpendicular to the disk at close to the speed of light, begins to push back against the infalling gas. The jets are among the most extraordinary structures in the universe. They emerge from the regions just outside the event horizon, collimated by magnetic fields, into narrow beams of plasma moving at fractions of the speed of light, and they can extend for hundreds of thousands of light years, far beyond the boundaries of the galaxy itself, before they eventually slow and spread into enormous lobes of radio-emitting plasma, called radio bubbles. The jet of M87, the same galaxy whose black hole was imaged in 2019, extends for approximately 5,000 light-years and has been observed since the early 20th century. It was first photographed in 1918 by Heber Curtis, who described it as a curious straight ray. He had no idea he was looking at the most energetic continuous structure produced by a single object in the observable universe. These jets carry energy from the black hole's immediate vicinity and deposit it into the galaxy and beyond. And that energy deposition has consequences for the gas that might otherwise cool, condense, and form new stars. Here is the cycle in its self-regulating form. Gas cools and flows inward toward the galactic center, feeding the black hole. The black hole grows more luminous, launching jets and winds. Those jets heat the surrounding gas, inflating radio bubbles that push the gas outward and prevent it from cooling further. The supply of infalling gas diminishes. The black hole's feeding rate drops. It becomes less luminous. The jets weaken. The surrounding gas, no longer being heated, begins to cool again. It flows inward. The cycle repeats. The black hole is breathing, slowly on timescales of millions of years, but rhythmically, in a cycle of activity and quiescence that regulates the temperature and density of the gas in and around the galaxy. It is not simply consuming the gas around it, it is thermostating it, keeping it at a temperature too high for widespread star formation, preventing the galaxy from converting all its gas into stars too quickly. The evidence for this process is direct and observable. In galaxy clusters, X-ray observatories have mapped the hot plasma gas at temperatures of tens of millions of degrees that fills the space between galaxies. In the most massive clusters, this plasma should be cooling. The temperatures suggest that within a few 100 million years, the gas should have cooled enough to fall into the central galaxy and trigger enormous bursts of star formation. But in most cases, it does not. The central galaxy remains relatively quiescent, its star formation rate far below what the cooling gas should be producing. When astronomers looked more carefully at the X-ray images, they found the explanation embedded in the structure of the plasma itself. Cavities. Enormous spherical regions where the X-ray emission was reduced, sometimes dramatically compared to the surrounding gas. These cavities are the radio bubbles inflated by the jets from the central black hole. They are holes in the hot gas carved by the energy output of the black hole, like bubbles rising through water. The jets push the gas aside, creating regions of lower density and lower X-ray emission, and in doing so they deposit their energy into the surrounding medium, heating it and preventing it from cooling. In the Perseus cluster, one of the most studied galaxy clusters in the sky, the X-ray observations from NASA's Chandra X-ray Observatory revealed a series of these cavities, concentric rings of alternating dense and rarefied gas extending outward from the central galaxy NGC 1275. Astronomers translated the pressure waves in that gas into sound, not literally audible sound. Since sound requires a medium denser than the intergalactic plasma, and the frequencies involved are far below human hearing, about 57 octaves below middle C, and found that the black hole at the center of NGC 1275 had been generating pressure waves in the surrounding gas for hundreds of millions of years. The universe's lowest note played by a black hole on the gas of a galaxy cluster. The black hole is not simply sitting at the center of the galaxy, it is communicating with the galaxy. Not in any intentional sense, it has no intentions, it has no awareness, but through the physics of energy and pressure and heat, its behavior propagates outward across hundreds of thousands of light years and shapes the environment that surrounds it. Nothing escapes it, not even light. And yet its influence extends to the very edges of the galaxies that host it. The implications of AGN feedback for our understanding of galaxy evolution are profound. Without it, computer simulations of galaxy formation produce galaxies that are far too massive, far too bright, far too blue. The simulations that include AGN feedback that allow the central black hole to heat and expel gas to regulate the star formation rate, to prevent the galaxy from converting all its gas to stars in a single early burst, produce galaxies that match what we observe: the right masses, the right luminosities, the right colors, the right distributions of stellar ages. AGN feedback is not a detail of galaxy formation. It is one of its central mechanisms. Remove it from the simulations, and the virtual universe looks nothing like the real one. Consider what this means for the existence of a galaxy like the Milky Way. Our galaxy has been forming stars at a moderate, sustained rate for most of its history. It has not exhausted its gas in a single catastrophic burst of star formation as some galaxies do. It has not been completely quenched, its star formation shut off entirely as other galaxies are. It sits in a middle state, still producing new stars at a rate of a few solar masses per year. Its gas supply depleted but not exhausted, its spiral structure maintained, its long-term habitability preserved across billions of years. That moderation did not happen by accident. The feedback from Sagittarius A star during the periods when it was actively feeding during the early epochs of the Milky Way's history, when the black hole was growing and luminous, and during more recent periods of enhanced activity, helped regulate the galaxy's gas supply. It helped prevent runaway star formation that would have consumed the available gas too quickly and left the galaxy red and dead billions of years ago. It helped maintain the conditions under which a moderate, sustained, chemically enriching cycle of stellar birth and death could continue long enough for second-generation and third-generation stars to form. Stars like the Sun, stars enriched with the heavy elements produced by previous generations, stars around which rocky planets could form, planets with the right chemistry for life. The black hole that sits at the center of your galaxy, the one you cannot see, the one whose shadow has now been photographed, the one that Karl Schwarzschild calculated from a trench in the First World War, is part of the reason you exist. Not by design, not through intention, but through physics, through the simple, inexorable consequence of mass and energy, and the feedback between an active nucleus and the galaxy it inhabits. The violence of the black hole, the jets it launched, the gas it heated, the star formation it regulated across billions of years, is woven into the conditions that made the Milky Way the kind of galaxy where life had time to emerge. You are in a very real sense the downstream consequence of a black hole's hunger. That inversion from destroyer to architect, from consuming darkness to the mechanism that made complexity possible, is one of the deepest and most disorienting realizations that modern astrophysics has produced. It requires a fundamental revision of the narrative we tell about black holes. They are not simply endings, they are in their indirect and physical and entirely non-intentional way beginnings. But the story of what black holes make possible does not end with the galaxies they regulate. It continues outward, into the interactions between galaxies, into the mergers and collisions that drive the universe's large-scale evolution. And it continues in another direction too, downward in time, toward a future so distant that the numbers involved to lose their meaning toward an epoch when the universe's current chapter of stars and light and complexity is long over. In that future, black holes play a final role, not as architects, not as regulators, but as the last structures standing when everything else has faded. To understand that role, we first have to understand what happens when black holes themselves collide. When two of these objects, these regions of space-time so distorted that nothing can escape, meet each other, when the event horizons merge, when the singularities combine, when two black holes fall together, they do not produce light. They produce something else entirely, something that travels not through electromagnetic fields, but through the fabric of space-time itself. Something that was predicted by Einstein's equations in 1916 and not detected until a century later in an experiment so sensitive it could measure a displacement smaller than 1/10,000th the diameter of a proton. They produce gravitational waves, and the story of how we first heard them is one of the most extraordinary episodes in the history of science. On the morning of the 14th of September, 2015 at 5:51 a.m. Eastern Daylight Time, a detector in Livingston, Louisiana, registered a signal. The detector is called LIGO, the Laser Interferometer Gravitational Wave Observatory. It consists of two L-shaped tunnels, each arm 4 kilometers long, meeting at a right angle. Inside those tunnels, laser beams travel back and forth between mirrors suspended by glass fibers, thinner than a human hair, isolated from the ground by systems of pendulums and vibration dampers, so sophisticated that the mirrors are among the most isolated objects ever constructed by human beings. The entire apparatus is designed to detect a single thing, a change in the length of its arms, so small it defies ordinary comprehension. The signal that arrived at 5:51 a.m. on the 14th of September 2015 changed the length of LIGO's arms by approximately 1/10,000th the diameter of a proton. A proton is roughly 1 femtometer across, 1/1,000,000th of 1/1000,000th of a meter. 1/10,000th of that is a number so small that writing it as a decimal requires placing the digit 1 after 16 zeros following the decimal point. It is not a distance that can be meaningfully visualized. It is smaller than the scale at which our current understanding of space itself remains coherent. LIGO measured it anyway. 7 milliseconds later, a second LIGO detector in Hanford, Washington, registered the same signal. The 7-millisecond delay between the two detections is consistent with a signal traveling at the speed of light from a direction in the southern sky. The two detectors, separated by 3,000 kilometers, serve as confirmation for each other. A real signal from space arrives at both. A local disturbance, a passing truck, a minor tremor in the ground, a fluctuation in the power supply affects only one. This signal affected both. It was real. The signal lasted approximately 0.2 seconds. In those 0.2 seconds, it swept upward in frequency from roughly 35 Hz to approximately 150 Hz, a rising chirp that, when translated into audible sound, is over in less time than it takes to say a single syllable. A brief ascending tone, a whisper in the structure of space-time that had been traveling for 1.3 billion years before it arrived at two tunnels in Louisiana and Washington and moved their mirrors by a distance smaller than any instrument had ever before measured. What produced it was the merger of two black holes, one with a mass of approximately 29 solar masses, the other with a mass of approximately 36 solar masses. They had been orbiting each other for an incomprehensible span of time, gradually losing energy through the emission of gravitational waves, ripples in the fabric of space-time produced by accelerating masses predicted by Einstein's general theory of relativity in 1916, but never directly detected in the century that followed. As they radiated energy, their orbit shrank. They spiraled closer. Their orbital period shortened. The gravitational waves they emitted grew stronger and higher in frequency. In the final fraction of a second before merger, they were orbiting each other at a significant fraction of the speed of light, separated by a distance smaller than the diameter of a large city, generating gravitational waves that carry more power than the combined light output of every star in the observable universe. Then they merged. The two event horizons touched combined oscillated briefly as the resulting black hole settled into a stable configuration, a process called ringdown, in which the distorted geometry of the new black hole vibrates like a struck bell, radiates the excess energy as a final burst of gravitational waves, and then fell silent. The resulting black hole had a mass of approximately 62 solar masses. But 29 plus 36 equals 65, not 62. 3 solar masses of matter were not present in the final object. Those 3 solar masses were converted entirely to energy in the form of gravitational waves during the merger. 3 times the mass of the Sun transformed into ripples in space-time in a fraction of a second radiated outward at the speed of light in every direction. By the time those ripples reached Earth 1.3 billion years later, they had spread across a sphere 2.6 billion light-years in diameter. The energy had diluted across that enormous volume. And yet even so, even after 1.3 billion years of spreading and diluting, the distortion they produced in the fabric of space-time near our planet was detectable. That detection was not accidental. It was the culmination of more than 40 years of effort. The possibility of detecting gravitational waves had been discussed since the 1960s, when physicist Joseph Weber built the first instruments intended to measure the metal cylinders called resonant bar detectors, designed to ring like a bell if a gravitational wave passed through. Weber announced detections in the late 1960s and early 1970s that generated enormous excitement before subsequent analysis, and the failure of other groups to replicate his results cast doubt on his claims. The field was set back. The waves were real in theory. Detecting them was another matter. The indirect evidence that gravitational waves existed came in 1974, when Russell Hulse and Joseph Taylor discovered a binary pulsar system, 2 neutron stars orbiting each other, one of them a pulsar emitting radio beeps with clockwork precision. By timing those beeps over years and then decades, they showed that the orbital period of the system was decreasing at precisely the rate predicted by general relativity. If the system were losing energy through gravitational wave emission, the 2 neutron stars were spiraling toward each other at exactly the rate Einstein's equations demanded. Hulse and Taylor received the Nobel Prize in Physics in 1993 for this work. It was compelling indirect evidence, but it was not a detection. The direct detection required instruments of sensitivity so extreme that building them required solving engineering problems that did not exist as defined problems before the project began. LIGO's development, led by Kip Thorne at Caltech and Rainer Weiss at MIT, both of whom would share the 2017 Nobel Prize in Physics for the detection, spanned decades. The project required not merely better mirrors and better lasers, but entirely new approaches to vibration, isolation, to vacuum technology, to the statistics of noise analysis, to the control systems required to maintain the optical cavities in which the laser light bounced back and forth millions of times, multiplying the effective path length from 4 kilometers to effectively hundreds of kilometers. The mirrors at the ends of LIGO's arms are among the smoothest objects ever manufactured. Their surfaces deviate from a perfect sphere by less than 1/10 millionth of a millimeter across their entire 34-centimeter diameter. They are suspended in a vacuum better than that of interplanetary space. They are isolated from the ground by a system of pendulums that reduces seismic noise by a factor of more than 1 billion at the frequencies of interest. And they must be held in precise alignment with each other, to tolerances that would have seemed impossible to maintain when the project was first proposed. It took until 2015, when LIGO completed an upgrade to its advanced configuration that improved its sensitivity by roughly a factor of 10. The upgrade was completed in September 2015. The first observing run of advanced LIGO began on the 12th of September 2015. 2 days later, at 5:51 inches the morning, the signal arrived. It arrived in a sense that carries its own kind of irony during an engineering test. The formal observing run had not yet fully begun. The detectors were running, the data was being recorded, but scientists had not yet confirmed that all calibrations were fully verified. The signal, the first gravitational wave event ever detected, designated GW150914 for its date, arrived almost before anyone was ready for it. As if the universe had grown impatient with the 40 years of preparation and decided to announce itself. The scientists who first saw the signal were not immediately certain it was real. Signals of various kinds appear in gravitational wave detectors constantly. Anthropogenic noise from human activity, seismic events, thermal fluctuations in the mirrors and suspensions, instrumental artifacts of countless kinds. The analysis pipeline that searched for signals buried in the noise was designed to be skeptical. It required careful statistical analysis, comparison between the two detectors, and an assessment of the probability that the observed coincidence could have arisen by chance. There was also a complicating factor that the LIGO collaboration had put in place deliberately blind injections. Fake signals introduced into the data stream by a small group of team members without the knowledge of the rest of the collaboration to test whether the analysis pipeline could correctly identify and characterize them. When GW150914 appeared, some scientists initially assumed it might be a blind injection. It was too clean, too clear, too nearly perfect a match to the theoretical predictions for a binary black hole merger to feel entirely real. It was not a blind injection. The team that managed the blind injection program confirmed this within days. What they had detected was real. It had come from space. It was a gravitational wave. The announcement, held on the 11th of February 2016 at the National Press Club in Washington, D.C., was preceded by weeks of rigorous internal review and followed by a global eruption of scientific excitement. The detection confirmed the last major, untested prediction of general relativity. It opened an entirely new window on the universe gravitational wave astronomy, through which phenomena that produce no electromagnetic radiation could now be observed directly, and it confirmed, with the directness that only experimental physics provides, that black holes exist as binary systems, that they merge, and that the geometry of space-time ripples when they do. Nothing escapes it, not even light, but the merger itself, the moment of collision between two event horizons, sends its signature outward through space-time at the speed of light, readable by instruments patient and sensitive enough to hear it. Since that first detection, the LIGO collaboration and its European counterpart Virgo have detected dozens of gravitational wave events, binary black hole mergers, binary neutron star mergers, and systems containing one of each. Each detection is a new data point in the study of compact objects, a new confirmation that general relativity describes the behavior of space-time under extreme conditions with extraordinary accuracy, and a new window into the population of black holes distributed through the universe. In August 2017, LIGO and Virgo detected the merger of two neutron stars. This event, designated GW170817, was accompanied by a short gamma-ray burst detected by the Fermi and Integral Space Telescopes 1.7 seconds after the gravitational wave signal. In the days that followed, telescopes around the world and in space observed the optical infrared, ultraviolet, X-ray and radio afterglow of what is called a kilonova, the explosive event produced by neutron star mergers, in which the collision of two neutron stars synthesizes heavy elements through a process called rapid neutron capture, or the R process. The gold in any ring you might wear, the platinum in any catalyst you might use, the uranium in any nuclear reactor. These elements, too heavy to be produced in ordinary stellar fusion or in supernova explosions, are synthesized in the collisions of neutron stars. We watched one of those collisions happen in real time, across 17 observatories and space telescopes simultaneously in gravitational waves, and in light for the first time in the history of science. The merger of compact objects does not merely confirm our physics, it makes the atoms of which we are partly composed. But the gravitational wave story has a chapter that extends far beyond the detection of individual mergers. It extends to a background signal, a hum of gravitational waves produced by all the binary mergers occurring throughout the universe, overlapping and accumulating into a stochastic background that fills all of space the way the cosmic microwave background fills all of space with ancient photons. In 2023, multiple pulsar timing array collaborations around the world announced evidence for exactly this background. The gravitational wave signal detected not through laser interferometry, but through the precise timing of millisecond pulsars, scattered across the galaxy, which serve collectively as the arms of a galaxy-scale gravitational wave detector. The universe hums with the mergers of black holes and neutron stars. The fabric of space-time is never entirely still. It ripples constantly with the accumulated energy of compact objects, spiraling together across cosmic time, their mergers, too numerous and too distant to resolve individually, but collectively, producing a signal that permeates all of space, deep background vibration in the geometry of reality itself. We are now in a position to hear it. The technology that made that possible, the mirrors smooth beyond any previous manufacturing capability, the vacuums purer than interplanetary space, the vibration isolation systems that filter out the noise of a living planet, the algorithms that search for coherent signals buried in data dominated by noise, represents one of the most sustained and precise engineering achievements in human history. It was built to answer a single question: do gravitational waves exist? The answer, delivered at 5:51 a.m. on the 14th of September 2015, was unambiguous. They exist. The universe speaks in them, and we have learned only in the last decade to listen. But the gravitational wave story, as remarkable as it is still a story set in the present universe. In a universe still lit by stars, still populated by galaxies, still rich with the gas and energy that feed both star formation and black hole growth. The full story of what black holes are and what they will ultimately become requires looking further, much further, beyond the current epoch of starlight, beyond the death of the last star, beyond the cooling and darkening of the universe to temperatures and densities that no current civilization will survive to observe. In that ultimate darkness, black holes remain. They are the last structures standing, and their eventual fate, the endpoint of Hawking evaporation across timescales so vast, they make the current age of the universe seem like a preliminary breath, defines the final chapter of everything that has ever existed. That chapter is not destruction. It is, in its own way, something stranger than destruction. It is completion. 0848, Claude responded. The sun will die. The sun will die. This is not a metaphor or an approximation. It is a physical certainty, as certain as anything in science derived from the same stellar physics that explains why the sun shines today. In approximately 5 billion years, the hydrogen in the sun's core will be exhausted. The fusion reactions that have sustained it for the past 4.5 billion years will falter. The core will contract under gravity, while the outer layers expand, swelling into a red giant that may extend as far as the current orbit of Earth. The inner planets will be consumed or scorched beyond recognition. Eventually, the outer layers will drift away as a planetary nebula, leaving behind a white dwarf, a dense, hot remnant the size of Earth, but the mass of a star, glowing with residual heat, slowly cooling over billions of years into darkness. Every star in the Milky Way will follow some version of this story. The most massive will end in supernovae, leaving behind neutron stars, or black holes. The least massive, the red dwarfs that make up the majority of stars in the galaxy, burn their fuel so slowly that the smallest of them will continue to shine for 10 trillion years, 10,000 billion years, more than 700 times the current age of the universe. But eventually even they will go out. There is a period in the far future that cosmologists call the stelliferous era, the age of stars. It is the era we currently inhabit, the epoch during which the universe is lit by the nuclear fusion occurring in hundreds of billions of galaxies across the observable cosmos. It began shortly after the Big Bang, when the first stars ignited from the primordial hydrogen, and it will end in the extremely distant future when the last red dwarf exhausts the last of its fuel and fades into a cold, dark cinder drifting through space. The stelliferous era will last in total approximately 100 trillion years, one followed by 14 zeros. a number that makes the current age of the universe, 13.8 billion years, seem like the opening seconds of a film measured in geological epochs. We are in the timeline of all possible stellar existence extraordinarily early. The universe is by the measure of how long stars will exist, barely a few % through the age of light. When the last star goes out, the universe will enter the degenerate era. The galaxies by then long since merged, within their local groups and clusters, the expansion of space having carried all other structures beyond the cosmic horizon, leaving each cluster an isolated island in an expanding void, will consist of cold remnants, white dwarfs cooling toward black dwarfs, neutron stars spinning down into silence, brown dwarfs that never quite ignited, and black holes sitting at the centers of what were once galaxies, their masses unchanged, their event horizons intact, waiting. Black holes do not age the way stars age. They have no fuel to exhaust, no internal pressure to maintain against gravity's pull. The singularity at the center does not evolve or decay in any way that current physics can describe. The event horizon persists. The gravitational field persists. In a universe where every other structure eventually changes, cools, fades, or transforms, a black hole simply continues to be what it is, but not forever. Hawking radiation, that quantum mechanical process by which the uncertainty of the vacuum near the event horizon allows particles to escape at the cost of the black hole's own mass, is real. It is extraordinarily slow. The rate at which a black hole loses mass through Hawking radiation is inversely proportional to the square of its mass. The larger the black hole, the slower it evaporates, and the temperature of the radiation it emits is inversely proportional to its mass as well. A black hole with the mass of Sagittarius A star, 4 million times the mass of the Sun, emits Hawking radiation at a temperature of approximately 1.5 times 10 to the negative 14th Kelvin. That is 0.00000000000000015 degrees above absolute zero. So cold that the surrounding universe, even in the degenerate era, will likely be warmer than the radiation the black hole emits, meaning it will absorb more energy from its environment and tenet, oozes through evaporation. Black holes do not begin to evaporate in earnest until the universe cools below the temperature of their own Hawking radiation. For supermassive black holes, that moment lies incomprehensibly far in the future. To speak meaningfully about the timescales involved requires abandoning the ordinary language of years and reaching for notation that compresses numbers too large to write in the normal way. A stellar mass black hole of 10 solar masses will take approximately 2 times 10 to the power of 74 years to evaporate completely. That is, a 2 followed by 74 zeros. The current age of the universe is approximately 10 to the power of 10 years. The evaporation time of a stellar mass black hole exceeds the current age of the universe by 64 orders of magnitude. A supermassive black hole of 1 billion solar masses will take approximately 2 times 10 to the power of 96 years to evaporate. A black hole of the mass of IC 1000, 101 central engine, perhaps 40 billion solar masses, will take timescales approaching 10 to the power of 100 years. These numbers are not physically meaningful in the way ordinary numbers are. They exceed by many orders of magnitude the timescales over which any current structure in the universe will remain intact. The proton itself, if proton decay occurs as some extensions of the standard model of particle physics suggest, may have a lifetime of roughly 10 to the 34th years. If protons decay, then all ordinary matter, every atom in every white dwarf and neutron star and cold planetary remnant, will have dissolved into radiation and lighter particles long before the supermassive black holes complete their evaporation. In that scenario, the black holes would be the only remaining structures in the universe, not merely the largest or the most massive, the only ones. The sole remnants of the stelliferous era drifting through an expanding void populated by nothing but radiation, and the occasional particle produced by their own Hawking evaporation, slowly losing mass over timescales that exceed all previous cosmic history by factors that language cannot comfortably hold. Nothing escapes it, not even light, except given enough time, enough time to make the entire previous history of the universe vanish as a rounding error, it all escapes. Slowly in the form of thermal radiation too cold to carry any organized information about what fell in the black hole returns its mass to the universe, particle by particle, photon by photon, across timescales so vast that the concept of waiting loses meaning. This is the endpoint of the black hole information paradox given physical form. Whatever fell in stars, planets, gas, clouds, the remnants of ancient civilizations, if any existed, the atoms that once composed living things, was compressed to a singularity that current physics cannot describe, held behind an event horizon, that current physics cannot see through, and eventually returned to the universe as featureless thermal radiation that current physics cannot decode. Whether the information is truly lost or merely scrambled beyond any practical recovery is the question that remains unresolved. But the evaporation happens, and when the last supermassive black hole completes its evaporation, when the final Hawking photon departs from the last event horizon in the universe, what remains is radiation, a universe of photons and neutrinos, and perhaps gravitons expanding forever, cooling forever, approaching absolute zero asymptotically, but never reaching it. No structures, no gradients of energy large enough to drive any process, no complexity, no information processing of any kind. This state is called heat death, the maximum entropy state of the universe, the condition in which no further work can be extracted from any energy difference because all energy differences have been smoothed away. It is not a dramatic ending. There is no explosion, no collapse, no final cataclysm. There is only an infinite, expanding, cooling uniformity. A universe that has, in the most complete sense possible, run down. The last black hole evaporating is the last event. After it, there are no more events. There is no after, in any meaningful sense. Time continues if the concept retains meaning in the absence of any process to measure it. But nothing happens in it. The universe has completed itself. That endpoint so distant that no number written in ordinary notation can convey its remoteness is the context in which black holes exist. They are not merely the most extreme objects in the current universe. They are the final chapter of the universe's physical story. Every star that forms every galaxy that assembles, every merger and collision and burst of star formation that fills the stelliferous era with light, is in the longest possible view a prelude to the era of black holes. The age of stars is the bright opening of a story whose conclusion is written in Hawking radiation too cold to feel emitted across timescales, too long to name, in a universe too empty to contain any witness. Nothing escapes it, not even light. But in the end, through the patient quantum mechanics of the vacuum, even the black hole itself returns what it took. The universe gets it back, in a form so dispersed and so cold that nothing useful can be done with it but back nonetheless. There is something in that fact that resists easy interpretation. It is not comforting in any simple way. The timescales involved are so vast that they are practically indistinguishable from infinity for any purpose that matters to living things. The information that might theoretically be recovered from the Hawking radiation of an evaporating black hole is for all practical purposes gone. The complexity that made the universe interesting, the stars, the galaxies, the chemistry, the life is dissolved into uniformity long before the last black hole completes its work. And yet, the black hole does not win in some final accounting. The event horizon that seems so absolute, the boundary that nothing could cross from the inside, the darkness that swallowed light itself, it is not permanent. It is only extremely long-lived. The universe's patience exceeds even the patience of a black hole. Given enough time, which the universe has in quantities that exceed all ordinary measure, even the inescapable becomes escapable. Even the event horizon is temporary. That idea that the most absolute boundary in nature is not on the timescale of the universe's full existence, truly absolute, is one of the strangest and most quietly significant conclusions of modern theoretical physics. It does not comfort the things that fell in. It does not recover the information in any usable form. It does not change the experience of crossing the horizon, which is for anything that does so final in every practical sense. But it means that the universe in its totality, across all of time, is a closed system that loses nothing permanently. Matter becomes energy. Energy becomes radiation. Radiation cools and disperses. And the black holes that seem to stand apart from all of this consuming without releasing, holding without returning, they too eventually give back what they took. Nothing escapes it. Not even light. Except in the end, everything does. What remains after that is a question physics cannot yet answer, and may never answer. The heat death of the universe, the state of maximum entropy, the condition of absolute uniformity, whether that state persists forever, whether some quantum fluctuation of sufficient magnitude eventually nucleates a new region of low entropy, whether the universe in some sense begins again, these questions sit beyond the edge of current knowledge. They may sit beyond the edge of any possible knowledge in a universe that has erased all record of its own history. We do not know what happens after the last black hole evaporates. We do not know if after is a concept that applies. We know only that it will happen on timescales that make the whole of cosmic history to this point appear as the very first instant of a story measured in eternities. And we know that right now in the brief and extraordinary middle of that story, we are here, aware of it, capable of tracing its arc from the first stars to the last evaporation, capable of building instruments that measure the ripples left by colliding event horizons, capable of photographing the shadow of a singularity 55 million light-years away, capable of asking what it means. The black holes are real, the event horizons are real, the Hawking radiation is real, though we have not yet detected it directly. The gravitational waves are real, and we have heard them. The feedback that shaped our galaxy and made our existence possible is real, written into the structure of the Milky Way and every other galaxy we have ever studied. The darkness that seems to consume everything is in the longest view part of a cycle. Not a comforting cycle, not a cycle designed with us in mind, not a cycle that promises any continuation of the things we care about, but a cycle nonetheless. Matter to stars, to black holes, to radiation, to something we cannot yet name. We are in the stars part, the brief, luminous, extraordinary stars part. And from that position, with the instruments we have built and the mathematics we have inherited and the curiosity that seems to be the defining feature of minds that emerged from the same astrophysics that produced everything else we can see dimly but truly the shape of the whole, that is where we have arrived. And it is from here that the final question opens. Not what black holes destroy, not even what they build, but what it means for us, for our understanding of the universe, for the strange fact that matter arranged itself into beings capable of comprehending the event horizon, that all of this is true. That question has no equation, but it has an answer of a kind, and it is the answer that this journey has been building toward from the beginning. 0850, Claude responded. Come back for a moment to the beginning. Come back for a moment to the beginning. There is something waiting at the center of your galaxy. 4 million times the mass of the Sun compressed into a volume smaller than the distance between the Earth and Mercury. You cannot see it. No light escapes it. No signal of any kind crosses its event horizon outward. It sits in the dark at the core of the Milky Way, surrounded by stars orbiting it at thousands of kilometers per second, and it has been there in some form for most of the galaxy's history. Longer than the Earth has existed, longer than the Sun has burned. When we started, that fact felt like a threat, like the universe had placed something dangerous at the heart of everything. Like the galaxy we call home was built around a consuming darkness that defined itself by what it took. Now, we know what it actually is. It is the reason the Milky Way has the structure it has. It is part of the reason the galaxy's star formation has been moderate and sustained rather than catastrophic and brief. It is connected through chains of physics that took decades to unravel to the conditions that allowed a second and third generation of stars to form stars enriched with heavy elements. Stars around which rocky planets could assemble, planets on which the chemistry of carbon and water and time could eventually produce something capable of looking back at the darkness and asking what it was. The black hole did not intend any of this. Intention is not a property of singularities. It simply existed and fed, and in feeding produced energy, and that energy propagated outward through the galaxy. It inhabited and shaped the environment in ways that physics demanded and that life eventually benefited from. The architecture was not designed, It emerged. From the same gravity that pulls everything inward came the jets and winds and feedback that pushed outward. From the consuming came the creating. From the darkness at the center came indirectly, and over billions of years, the conditions for light. That is what we have traced across this journey. Not a simple story of destruction, but a complex story of regulation. Not the universe's way of ending things, but one of its primary mechanisms for shaping them. The black hole at the center of the Milky Way is not an anomaly or an exception. It is a fundamental feature. Every large galaxy we have ever observed contains one. The correlation between black hole mass and galactic bulge mass, tight and consistent across the full range of galactic sizes, tells us that the two grew together, that they are not separate phenomena, but aspects of a single process, that the galaxy and its central black hole are, in a physical sense, same story told at different scales. We began also with a question about visibility, about how we can know that something exists when we cannot see it. That question has been answered in ways that would have seemed impossible a generation ago. We track the orbits of stars moving at thousands of kilometers per second around an invisible point at the galactic center and derive the mass and density of what must be there. We built an Earth-sized telescope from 8 radio observatories on 4 continents, collected petabytes of data, shipped hard drives by airplane from the South Pole, and reconstructed the first image of an event horizon, a ring of orange, light around a central darkness, exactly the shape that Einstein's equations predicted, located 55 million light-years away in the heart of the galaxy M87. We built interferometers sensitive enough to measure a displacement, 1/10,000th the diameter of a proton, and heard the gravitational wave chirp produced by 2 black holes merging 1.3 billion years ago, a signal that lasted 0.2 seconds and confirmed in that fraction of a second the last major untested prediction of general relativity. We know they are there. We have heard them. We have photographed their shadows. We have measured the ripples they leave in the fabric of space-time when they collide. Nothing escapes it, not even light. And yet everything we have learned about them has escaped outward into our understanding, carried not by photons crossing the event horizon, but by the gravitational signatures, the orbital mechanics, the radio waves and X-rays, gravitational waves that the regions around black holes produce in such abundance. The universe found ways to tell us about its darkest structures through everything that surrounds them. Consider what this means for the position we occupy. You exist in what cosmologists call the stelliferous era, the age of stars. The universe is approximately 13.8 billion years old. The last red dwarf will burn for another 100 trillion years. We are, by that measure, in the very early phase of the only era of cosmic history that produces the light and energy necessary for biology. The universe is young in the way that matters for living things. It is rich with stars, rich with the chemical complexity that stellar nucleosynthesis has produced over billions of years, rich with the planetary systems on which that chemistry can find expression. And within this era, on one particular planet, orbiting one particular star, in one particular spiral arm of one particular galaxy, a form of matter has arranged itself into beings that can build interferometers, develop general relativity, image event horizons, and hear gravitational waves. The same matter that emerged from the Big Bang as hydrogen and helium. The same matter that was processed through generations of stellar nucleosynthesis, enriched with carbon and oxygen and iron and calcium and every other element that life requires. The same matter that was dispersed by supernova explosions across light years of interstellar space, gathered again by gravity into new clouds, collapsed into new stars, accreted into new planets, and eventually over billions of years of biological evolution became capable of asking questions about the process that produced it. The black holes were part of that process. The supernova that scattered the atoms that became you were the endpoints of stellar lives that the black hole at the galactic center helped regulate. The galaxy that provided the stable, long-lived environment in which the sun could form and the Earth could persist long enough for evolution to produce complexity that galaxy has the structure. It has in part because of AGN feedback from the black hole at its center. The connections are real. They are physical. They are written in the structure of the Milky Way and in the chemistry of every living thing on Earth. You are downstream of a black hole in ways that go deeper than metaphor. But there is something else here, something that the physics alone does not fully capture. It is the fact of comprehension itself. Karl Schwarzschild solved Einstein's equations from a trench in the First World War and described a mathematical boundary from which nothing could return. He died before anyone knew whether the object he had described was physically real. Andrea Ghez and Reinhard Genzel spent decades photographing the same patch of sky, tracking the same stars, accumulating the same data, and demonstrated beyond reasonable doubt that the object is real, that it sits at the center of our galaxy, that it has been there for billions of years. The Event Horizon Telescope collaboration connected 8 observatories across the planet, coordinated the work of more than 200 scientists in 20 countries, and produced an image of something that a century ago was not known to exist and was not considered observable even by those who believed it did. These are not merely scientific achievements. They are demonstrations of something that has no obvious reason to exist in a universe governed by the laws of physics. They are demonstrations of the capacity of matter to understand itself, of the ability of atoms arranged in the particular pattern that constitutes a human mind to comprehend the behavior of atoms arranged in the extreme pattern that constitutes a black hole. The universe, in producing minds capable of this comprehension, has done something that its fundamental laws do not require and do not explain. The laws of physics do not demand consciousness. They do not demand curiosity. They do not demand that matter develop the capacity to wonder about its own origin and structure and fate. And yet here we are wondering. The black hole does not know it is being studied. The event horizon does not care that its shadow has been photographed. The gravitational waves that moved LIGO's mirrors by 1/10,000th, the diameter of a proton, were not sent as messages. They were not intended to be heard. They were simply the consequence of 2 massive objects following the geometry of space-time to its logical conclusion, merging and releasing their energy into the universe in the only form available to them. But we heard them. We built instruments specifically calibrated to hear them. We waited 40 years for the technology to reach the necessary sensitivity, and when the signal arrived at 5:51 inches the morning, on the 14th of September 2015, the mathematics and the measurement and the physics all agreed. The universe had spoken in the language of space-time distortion, and we had learned enough of that language to understand what it said. That is extraordinary. Not in a casual sense, but in the deepest sense available. It is extraordinary that the universe is comprehensible at all. It is extraordinary that the same physical laws that govern the behavior of black holes also govern the behavior of neurons, that the mathematics of general relativity is accessible to beings made of the atoms that general relativity describes, that the event horizon, which permits no information to escape, can nevertheless be understood from the outside by minds that never cross it. Einstein called the comprehensibility of the universe the greatest mystery. Not why the universe is so large, not why black holes exist, not why gravity curves space-time, but why any of it is understandable at all. Why the universe should be the kind of place that rewards investigation. Why the equations should be elegant. Why the predictions of mathematics derived in the abstract should correspond so precisely to the behavior of physical reality. That correspondence between human thought and cosmic structure is not something the physics explains. It is something the physics exemplifies. And it is from within that mystery that we look at black holes and see not simply destruction, but architecture. Not simply endings, but the regulation of beginnings. Not simply the darkness that swallows light, but the darkness that in swallowing shapes the conditions under which light can exist at all. The universe will end in a sense in black holes. They will be the last structures standing when the stars are gone, the last concentrations of mass and gravity in an expanding, cooling void. And then they too will evaporate through the patient quantum mechanics of the vacuum, returning their mass to the universe as featureless thermal radiation across timescales, so vast they make all of cosmic history to this point look like a preliminary breath. After that we do not know. But before that, in the long, luminous, improbable middle of the universe's story, there is this. A period when stars burn and galaxies turn and black holes regulate and rocky planets form around stable suns. And on at least one of them, in at least one spiral arm of at least one unremarkable galaxy, among 2 trillion matter wakes up, looks around and begins to understand what it is part of. That period is now. We are in it. You are in it at this moment on a planet whose atoms were forged in stars that lived and died before the sun existed, orbiting a star whose stability was shaped in part by the feedback of the black hole at the galactic center in a galaxy whose structure is the product of billions of years of physics that culminated among countless other things in the particular conditions that made your existence possible. The black hole has been waiting at the center of your galaxy for longer than the Earth has existed. It will be waiting there long after the sun goes out. In the context of what it is, a singularity in space-time, a region from which nothing escapes, a structure defined entirely by its impermeability to information, it is the most alien thing in the observable universe. And it is yours. It belongs to the same galaxy that belongs to you. The same gravity that holds it together, holds the stars that made your atoms. The same physics that makes it incomprehensible also makes it eventually, after enough patience and enough mathematics and enough instruments built with enough care, understood. Not fully, not yet. The information paradox remains open. The nature of the singularity remains beyond the reach of current theory. The question of what quantum gravity looks like, of what happens at the precise point where general relativity and quantum mechanics must both apply and cannot both be right in their current forms. That question remains the deepest unresolved problem in fundamental physics. But we know the shadow of the event horizon. We have heard the chirp of 2 merging black holes. We have watched stars orbit the invisible mass at the galactic center for decades and measured that mass to extraordinary precision. We have built the theory that predicted all of it from first principles from equations written by a man who thought the objects they described were probably not real. They are real. They are everywhere. They shaped the universe you inhabit. They will outlast everything that currently exists. And in the end, across timescales that no living mind will ever experience, they will give back everything they took. Nothing escapes it. Not even light. Except in the fullness of time, everything does. The darkness is not the end of the story. It is the part of the story we are still learning to read. And somewhere in the reading, in the decades of patient observation, in the 40 years of building instruments sensitive enough to hear space-time vibrate in the moment, a 29-year-old scientist watched an image assemble itself on a screen and recognized in its orange ring the shadow of something 55 million light-years away. The universe found a way to know itself a little better. Through us, through the matter that learned to wonder. The event horizon holds its silence. The Hawking radiation disperses into the cooling dark. The gravitational waves expand outward at the speed of light, carrying their message across the universe in every direction, growing fainter with distance, but never fully disappearing, crossing galaxies and voids and clusters in an expanding sphere that will not stop until the universe itself prevents its further travel. And here, on a small planet, in an ordinary galaxy, in the brief and luminous middle of the only era that produces starlight, we listened. That is enough. That is in the quiet arithmetic of meaning that the universe does not provide, but that we bring to it more than enough. The stars continue to burn. The black hole at the center of the Milky Way continues its patient vigil. The gravitational waves from ancient mergers continue their outward journey through space-time. And you made of the same matter as all of it, shaped by the same physics that shaped all of it, are here for a moment in the middle of all of it, aware of what surrounds you. A single point of comprehension in a universe that did not require it, burning quietly like a candle in a darkness that extends farther than light has traveled since the beginning of time.